All right, good morning, everyone. And it's time for us to begin our session. You are all welcomed to the 9th Meteorological Virtual Seminar Series, which we are really privileged this morning to have a resource personnel in the name of Dr. Derek Danso, who is a PhD postdoc at the Iowa State University, Ames, United States. A bit of introduction of Dr. Derek. He does research in regional climate variability and then focusing on local and then large scale drivers of climate extremes, clouds and then energy budgets. He has expertise in atmospheric physics, climate science, WAF, renewable energy, climate change, aerosol cloud climate interaction, regional climate variability, solar energy, hydrometeorology, synoptic climatology, cloud physics, climatology, reanalysis, satellite data and satellite data analysis, climate forecast system reanalysis, and then also regional climate modeling. Today, we are really privileged to have such an astute personnel to lead us in this presentation. And his topic for today is African easterly waves. Do they limit Atlantic tropical cyclone activity? It's really an interesting topic for discussion. So without much ado, I am going to allow Dr. Derek Danso to do his presentation. So Doctor, over to you. Audience, Dr.
Right.
Thank you.
Thank you, Samuel. I'm going to share my screen and then switch off my video so that.
Okay.
Right. So okay. So thank you once again for the introduction. Thank you for inviting me to share my research with the group. So I'm going to talk about something that I've been working on for the past 6 months, and the title of the presentation is in the form of a question, like Samuel said. So the title is: Do African easterly waves limit tropical cyclone activity in the Atlantic? Right. And so I'm going to begin by telling you what African easterly waves are, for the sake of those who might not know what African easterly waves are. Right. Basically, when you consider the northern part of Africa, or the northern hemispheric Africa, there are two different air masses that interact in the region. So there is a hotter air mass that is coming in from the Sahara deserts, as you can see over here. And then there is a cooler air mass that is coming in from the southern parts of the region. Now, the interaction of these two air masses generates what you call a thermal gradient or temperature gradient. And then again, the interaction of these two air masses generates what you call the African easterly jets. Now, the African easterly jets that you can see on this lower panel of figure here is basically an area of maximum wind speed in the lower to middle part of the atmosphere. Now, within the African easterly jets itself, there could be instabilities, and those instabilities could be as a result of an encounter with a topographic feature like a mountain or developing convection near the African easterly jets. And so when these instabilities occur, they generate some low pressure perturbations or low pressure disturbances that we call the African easterly waves, as you can see over here. Basically, I mentioned that the African easterly jets itself could have some instabilities within it. And those instabilities could be as a result of an encounter with a topographic feature like a mountain, or developing convections near the African easterly jets. And when these instabilities occur, they generate what we call the African easterly waves. So these African easterly waves are basically low pressure disturbances or low pressure perturbations that is formed as a result of instabilities in the African easterly jets. Now, these African easterly waves generate between latitude 5 degrees north and latitude 30 degrees north of tropical northern Africa, and especially during the summer months. And another thing that we have to know about these African easterly waves is that, as the name suggests, they are easterly waves. That means they are formed in the east and then they propagate towards the west, right? Now, there have been so many studies about these African easterly waves. And one of those studies I would like to talk about is something that I'm going to refer to in a later slide. So studies have shown that there are two different tracks of the African easterly waves. There is a first track of the African easterly waves that is found just north of the African easterly jets. So that's what we call the northern track of the African easterly wave. And there is a second track of the African easterly wave that is found just south of the African easterly jet. So that is what we call the southern track of the African easterly wave. I'm going to make reference to this in a later slide. So why are these African easterly waves important? The first thing that we have to know, and I believe is what is going to concern a lot of people in this presentation, is that they influence the weather of West Africa. Now, these African easterly waves are linked to convective rainfall, especially in the Sahelian part of West Africa. Now, I believe most of us here will remember that in 2009, there was a very strong intense flooding events that occurred in the Sahel region of West Africa, especially Ouagadougou, Burkina Faso, that claimed a lot of lives and then destroyed a lot of properties. Now, this intense flooding event that occurred in 2009 in Ouagadougou was actually due to a very strong African easterly wave that occurred together with some mesoscale convective systems, and they interacted together to produce this record-breaking rainfall that led to this intense flooding events that killed a lot of people and then destroyed a lot of properties. So these African easterly waves are important for the weather of West Africa. The second reason why these African easterly waves are important, and that is the focus of my presentation today, is that they serve as precursors for tropical cyclones in the Atlantic Ocean. Now, a tropical cyclone, as you can see on this satellite imagery here, is basically a storm that is rotating rapidly. And within the storm, there are very strong winds and then heavy rainfall. This is what we call a tropical cyclone. Now, depending on where the tropical cyclone is formed, it can be called different names. And in the Atlantic Ocean or in the Atlantic region, when tropical cyclones are formed, they are called hurricanes. And I believe we have all heard of hurricanes. Every year we hear of hurricanes, right? So these hurricanes lead to loss of lives and destroy a lot of properties every year, as we hear in the news. You can see from this short video the damage that it's causing to the building, right? So why do we say African easterly waves are precursors for these tropical cyclones in the Atlantic Ocean or hurricanes? Now, the first thing that we have to know is that we know already that most of the hurricanes that form in the Atlantic begin as easterly waves. That is coming off the western coast of northern part of Africa, right? So as these easterly waves, for instance, this is an easterly wave here. As these easterly waves move over the warm ocean surface, they gain a lot of energy from the heat that is coming off the ocean surface, and then they gain a lot of moisture. And when they gain this energy and moisture from the ocean surface, all right, so when these African easterly waves move over the warm ocean surface, like I said, they gain energy and moisture from the ocean surface and then develop into this tropical cyclones, as we are going to see in this animation. So this is the African easterly wave moving over the ocean, the warm ocean surface, and then it gains a lot of energy from it, becomes very violent, and starts to rotate. That is when it has reached tropical cyclone status. And then it travels all the way to the eastern coast of the United States, where it can cause a lot of damage and kill a lot of people. Right? So these African easterly waves are important precursors for these tropical cyclones or hurricanes, as we call them. Right? Now, when it comes to the relationship between African easterly waves and tropical cyclones, we know there is a very strong link between the two on synoptic timescales. When I talk about synoptic timescales, what I mean is several hours to a few days. There is a very strong connection between these African easterly waves and then the tropical cyclones that occur in the Atlantic Ocean. But when it comes to the relationship on climate timescales, when I talk about climate timescales, what I refer to as the interannual timescales or the seasonal timescales. When it comes to the relationship at these timescales, they are still unclear at this point. Right. For instance, there has been a study that have shown the interannual variability of African easterly waves and tropical cyclones. So, for instance, on this figure, we have the internal variability of African easterly waves that is shown as the solid line. And then we have the internal variability of different classes of tropical cyclones, that is the dashed lines. Right? You can see in some years, there is a very high amount of African easterly waves, but then there is a low number of tropical cyclones. So this is like a negative correlation, something like that. But then in some other years, we see there is a high number of African easterly waves, and there is equally a high number of tropical cyclones, right? So in some years, there are positive correlations between African easterly waves. In other years, there are negative correlations in African easterly waves and their tropical cyclones relationship. And so because of these, there have been questions asked over the years whether tropical cyclones in the Atlantic Ocean are limited by African easterly waves on the seasonal basis or interannual basis. Right? And so to try to answer some of these questions, we use regional climate model experiments to try to answer some of the questions. And some of the questions we answered is whether the absence of African easterly wave will limit the seasonal frequency of tropical cyclones or not. And then the second question that we try to answer with this regional climate model experiment is what environmental conditions will drive tropical cyclone formation in the absence of African easterly waves, right? So we have used the weather research and forecasting model, the WRF model, which is a very popular model among the meteorologists and then the atmospheric scientists. So the first thing that we have done is to design a model domain. So because tropical cyclones in the Atlantic Ocean, of course, we have made sure that the model domain covers most of the northern part of the Atlantic Ocean. Right? And what we did is we tried to extend the eastern lateral boundary of the model to get to the western coast of northern part of Africa. All right, and this western coast of northern Africa is where the African easterly wave will move from West Africa into the Atlantic Ocean, where they can gain energy and become tropical cyclones, right? And so after designing the model domain, we made the control simulation. And when I talk about the control simulation, what I mean is we simulated the climate as it is. We don't change anything. We just simulated the climate as it is. So this is called the control simulation, or you can also call the reference simulation. So we are going to compare the result that we find in this control simulation to other simulations that we made, right? After making this first control simulation, we did an experiment. Right? The experiment is that I already mentioned, we put the model domain, the eastern lateral boundary of the model domain, just off the coast of West Africa, and the coast of the western coast of North Africa, right? So we put a digital filter at that place. We put a digital filter at the western coast of West Africa or northern part of Africa. Right? What this filter does is that it suppresses the African easterly waves that are coming off the region and moving into the ocean. It suppresses them from getting into the ocean. Or in other words, it filters the African easterly waves from getting into the ocean. All right, where they can gain energy and then become tropical cyclones. So in this case, we have basically taken tropical cyclones out of the equation. And then we made the simulation for this as well. Right. Now, I have to acknowledge that this experimental design that I just described was first introduced and used in a study that was carried out in 2018 by Patricola and others. Now, Chris Patricola is also a professor at Iowa State University, where I'm currently working on this particular project with her. So I have to acknowledge the fact that she introduced this model design that I just described. Now, the Wolf model that we use to make the simulations requires that we input some information or some data before it can run the simulations. So for this Wolf model that we designed, the boundary conditions that we use as input data for the model were obtained from the error 5, the ECMWF analysis, that is called error 5. Error 5 has a horizontal resolution of approximately 31 kilometers, so it's really great. And then we designed our model to have a horizontal resolution of 3.5 kilometers. Now, 3.5 kilometers is a very high resolution, model. And so what we did is we used explicit convection. We solved convection explicitly in the model. We did not use parameterized convection. Now, in the study that Chris Patricola and others carried out in 2018, they set up the Wolf model to have a horizontal resolution of 27 kilometers. Now, 27 kilometers horizontal resolution, the convection cannot be solved explicitly. It has to be parameterized. So they use parameterized convection. Now, the problem with parameterized convection is that when you use in the models have difficulties in representing some very fine scale convective processes. And I'm going to show again the reason why we decided to use explicit convection and not parameterized convection. So as I mentioned in the beginning of the presentation, one of the mechanisms that can trigger these African Easterly waves is convection within the African Easterly jets. And so many studies have shown that the African Easterly waves themselves, the development of these Easterly waves themselves requires some kind of triggering mechanism, such as convection, in order to occur. So if you look at these two figures, this first figure that you see here shows the count of African Easterly waves over the region for a certain period of time. And then if you look on the right-hand side there, we have the areas of peak convection, again, over the region for a certain period of time. Now, if you look carefully, you can see there is some kind of spatial correlation between areas of peak convection and then the African Easterly wave counts, right? And so this shows that this African Easterly waves has a strong connection to convection. And so instead of using parameterized convection, we decided to solve convection explicitly so that we will be able to represent all of these fine scale convective processes in the model. Now, another thing that is different from the study that Chris Patricola carried out in 2018 is that they simulated the 2005 tropical cyclone season. Now, on record, the 2005 hurricane season is one of the most intense tropical cyclone seasons on record. But if you look at the storm tracks, these are the storm tracks of all of the tropical cyclones that were recorded in 2005. If you look at the storm tracks, you can see that they are all of them are further away from the western coast of Northern Africa, where the African Easterly wave enter the Atlantic Ocean. All right, so I'll begin here. So like I mentioned, they simulated the 2005 tropical cyclone season. Now, the 2005 tropical cyclone season is one of the most intense tropical cyclone seasons on record to date. But if you look at the storm tracks of all of the tropical cyclones that occurred in 2005, we can see that they are much further away from, they are formed much further away from the western coast of Northern Africa. And so somebody will argue that these storms or these tropical cyclones are not formed from African Easterly waves, because since African Easterly waves are coming off the coast of the western coast of Africa over here, we expect them to not be much closer to the region, but they are in this case further away from the western coast of Northern Africa. And so we decided in this new study to simulate the 2020 tropical cyclone season, which also happens to be one of the most intense tropical cyclone seasons on record. But if you look at the 2020 tropical cyclone season, we can see there are a number of tropical cyclones that are much closer to the western coast of Northern Africa. And so this is a very good case to simulate, because we can say now that some of these tropical cyclones are formed from African easterly waves. All right. Now, after making the simulations, one thing that you have to know is that the WRF model does not output tropical cyclones. It does not output any variable called tropical cyclones or hurricanes. It outputs other variables that we can use as proxies for tropical cyclone. So to detect tropical cyclones in the WRF simulations that we make, there are several algorithms that we can use to make calculations that will help us to detect these tropical cyclones, right? And one of those algorithms is one that was developed by Walsh in 1997. So it's a very efficient algorithm. That is why we decided to use this algorithm. What this algorithm does is, first of all, it looks over the study domain to find where we have a certain minimum vorticity threshold met. It looks for all places where a certain minimum vorticity threshold is met. After that, it looks around this minimum vorticity threshold point to find out whether a certain minimum pressure threshold is also met. So this is the first two conditions. Then, after finding the minimum pressure threshold, it looks around a certain area. It looks around a certain area around the minimum pressure point to find out if the minimum wind speed within that area is at least 17.5 meters per second. So when all these three conditions are met, then we now start considering that point as a possible or a potential tropical cyclone candidate, right? Now, I think there are 5 other conditions that are supposed to be met in order for us to say that this is finally a tropical cyclone. But I'm not going to go into detail since this is not really the main focus of my presentation. But for those who are interested in learning more about these algorithms, I'll kindly refer you to look at the Walsh 1997 publication, where he outlines all of these information. And for those who are interested in the code to do your analysis, you can contact me after this presentation, and I'm very happy to share with you this code. Right now, after making the simulations and then detecting the tropical cyclones, the next part of the analysis was to make an evaluation of the model. Right? Now, the evaluation that we made was just a comparison with what is observed, the observations, right? So for the observation data sets, we use the International Best Archive for Climate Stewardship, as it's called the IBTRACS. So the IBTRACS has information on tropical cyclones in all of the ocean basins around the world, right? So we took this IBTRACS data sets, and for the period that we made the simulation, that is from August to October 2020, we focus on October because this is the core season of the tropical cyclones. For that period, the observation data set had 16 tropical cyclones occurring. And then the WRF simulation, for the control simulation that I already talked about, also had 16 tropical cyclones. And so this is really good because we are having the same number of tropical cyclones. And then when you look at the monthly distributions, we can see there is some slight disparities. So for instance, in August, we have one less tropical cyclone in the WRF simulation than the observations. And then in September, we have one more in the WRF simulation than the observation. Now, this is not very big. This is a very slight disparity. And if you look at what we are seeing here, the model is actually performing really good in simulating this tropical cyclone seasonal number. So we went ahead and used this model for our analysis. Right now, I'm going to start talking about some of the results that we have so far. So the first thing I'll talk about is the response of tropical cyclone number to the suppression of African easterly waves. What happens after we suppress African easterly waves? So like I said, the control simulation had 16 tropical cyclones. After we suppressed the African easterly wave, we also had 16 tropical cyclones. Right now, this is very interesting because we've already seen, I've already mentioned that the tropical cyclones or the hurricanes that occur in the Atlantic Ocean are mostly formed by these African easterly waves. So it is very strange and interesting to see that even after cutting off the supply of these African easterly waves, we are still getting the same number of tropical cyclones as when the African easterly waves were present, right? So the first thing that we can see, the first conclusion that we can make from this particular result is that tropical cyclones will generate by other mechanisms in the absence of African easterly waves. And so the very first question that we asked in the title of the presentation, whether African easterly waves limit tropical cyclones, is answered now. African easterly waves do not limit the seasonal frequency of tropical cyclones in the Atlantic, right? And if this is the case, then we cannot say African easterly waves will be reliable predictors for future changes in tropical cyclone frequency, right? Because if somebody makes a projection with a climate model currently, right now, and tell us that, okay, in the next 100 years or in the next 50 years, African easterly waves are going to reduce by 50%, or they are going to reduce by 80%. We cannot base on that statement to say that, if this is the case, then tropical cyclones are also going to reduce, because like we see in this particular result, tropical cyclones were forming by other mechanisms in the absence of these African easterly waves. But then when you look at the monthly distributions of African easterly waves, when you look at the control simulation and then the suppressed simulation, we can see a very big discrepancy in the monthly distributions, right? We can see there's a distribution in all of the months over here. So with African easterly waves, that is the orange here, we have a certain pattern. That's the distribution follows. And then without African easterly waves, there's also another pattern, that's the distribution follows. What we can say from this figure here is that although African easterly waves may not influence the total number or the frequency of these tropical cyclones, they may have an influence on when or the timing of the tropical cyclone. When the tropical cyclone starts to form, they may have an influence on these, right? Now, I'm going to show on this slide the response of the tropical cyclone genesis location to the easterly wave suppression. Right. Now, when I talk about tropical cyclone genesis location, like the name suggests, genesis location, it is the location where the development of this tropical cyclone begins. So that is the genesis location. Now, on this first slide here, we are going to look at the genesis longitude. So the longitude where the tropical cyclone begins to generate, right? So on this figure here, we will look at the probability distribution, probability density distributions for the control simulation and then for the suppressed simulation. So we have the longitude on the x-axis, and we have the probability density on the y-axis. Now, what we can say from this figure is that when African easterly waves are suppressed, as is the green curve, there is a westward shift in the tropical cyclone genesis location, right? There is a westward shift. Now, you can see that on the eastern side of this longitude is 45 degrees west, I believe. So on the eastern side of this longitude, there is a reduction in the probability density of tropical genesis, or the genesis location of this tropical cyclone. What this basically means is that there is a reduction in number of tropical cyclones that can form on the eastern side of this longitude. Right? And this makes sense because if you remember, I mentioned that we filtered the African easterly waves around this area. This is the eastern part of the Atlantic Ocean. So we have filtered African easterly waves around this area. And so as we have taken African easterly waves out of this area, we do not expect a lot of tropical cyclones to form here. That is why we have this big reduction in the tropical cyclone genesis location. And then we can see that in the western part of the Atlantic Ocean, there is an increase in the number of tropical cyclones that can form over here. That is why I mentioned that there is a westward shift in the tropical cyclone genesis location, right? Now I'll talk about the next slide and I'll try to make a synthesis with this previous slide. So this slide talks about the genesis latitude. The previous was the genesis longitude, but we have the genesis latitude. So this is, on this axis we have the latitude, on the y-axis we have the probability density. Right, I'll first talk about the control curve. So we can see that we have, for the control simulation, we have two peaks. We have one peak between latitude 10 degrees north and then latitude 15 degrees north. And we have another peak around latitude 24 degrees north. If you remember in the beginning of the presentation, I did mention that there are two tracks of the African easterly wave. There's one track in south and then another track in the north. And two peaks that you see for tropical cyclone genesis latitude corresponds clearly to the two tracks of African easterly waves. We have the southern track of the African easterly waves helping to form tropical cyclones. This, and we have the northern track of these African easterly waves helping to form tropical cyclones. That's why we have these two peaks. What happens when you suppress these African easterly waves? Basically, what this slide is showing us with the previous slide is that although African easterly waves may not control the number of tropical cyclones that's formed, it could have an influence on the location of the tropical cyclone genesis, the location where tropical cyclones formed. Now, this result that I've shown here was also seen in the study that Chris Particular carried out in 2018. Right? So in their study, as I mentioned previously, they made the world simulation at 27 kilometers horizontal resolution. Now at 27 kilometers resolution, the simulation is not computationally expensive like 3.5 kilometers. So they were able to make several ensemble members, right? So on this slide, I will show, they show 4 different ensemble members for the control simulation. And this is like a time frame snapshot. So it's the snapshot that you see here covers a certain time frame, I think a week from 20th August to 27th August of 2005. Right? And you can see in all of the ensemble members for the control simulation, we can see a tropical cyclone that is traversing the Atlantic Ocean, right? And it seems like all of these tropical cyclones are following a systematic track. They all follow a certain path that is very similar within all of the 4 ensemble members. But then if we look at the suppressed simulation that they made for the same time frame snapshot, we can see there are some tropical cyclones, all right, and they are just all over the place. They do not follow any specific track. They do not follow any systematic track. And so these results that I showed in the two slides before this agrees with this result that Chris Particular found in 2018. So tropical cyclones, African easterlies may not influence the number, but they can have an influence on the location where the tropical cyclone genesis occurs, and also the location, the path or the track that is taken by the tropical cyclone. So this is a very important result that we found. Now I'll talk about the last bit of stuff before I bring my presentation to a close. So this next slide, I'm going to talk about the role of the sea surface temperature during the tropical cyclone's lifetime. Right. So on this figure here, what we compare is the sea surface temperature composite mean, right, for the control simulation and then for the suppressed simulation. Now, what is clear here is that when African easterly waves are suppressed, the tropical cyclones develop and evolve in warmer ocean conditions compared to when the African easterly waves are present. All right. So basically, we have, like we are seeing here, we have warmer ocean surface conditions, and here we have much cooler ocean surface conditions, right? But then let's look at the standard deviation. So on this right-hand side, we have the sea surface temperature composite standard deviation. Now, again, when you look at the suppressed simulation, we can see that it has very low standard deviation over all of the region. So this basically means the sea surface temperature has a low variation, right? Since we have warm ocean surface over here on the left-hand side, then we have low variation of the sea surface temperature. It means that when African easterly waves are suppressed, the sea surface temperature will remain warm throughout. Okay, it will not change so much because we have a very low standard deviation or low variation. But then in the control simulation, we see we have very high standard deviation. That means we have high sea surface temperature variation. And since we have cooler sea surface temperatures here, it means that sometimes the ocean surface will be cool, sometimes it might be warm. And that's why we have this big, a high standard deviation over here. Right now, to go more in this sea surface temperature contribution, we try to group the tropical cyclones that we had in each simulation into 3 categories. I'm not really going to go into detail about the physics and then the assumptions that we made in these groupings. I'm going to use these groupings to show something on the next slide about the sea surface temperature. So we try to group tropical cyclones based on the lifetime of the tropical cyclone, the strength of the tropical cyclone, the distance traveled by the tropical cyclone, and the speed with which it travels. That's why that's how come we were able to come up with all of these 3 groups, right? Now, when we look at the sea surface temperature composites mean for these 3 groups, one thing is very clear here. So again, I'll start from the lower panel. When we look at the suppressed simulation, when African easterly waves are suppressed, the sea surface temperature for all of the 3 groups is warm. We have warm sea surface temperature across all of the 3 groups, and they are very similar. There is not a lot of changes between the 3 groups. And when you look at the control simulation, we can see that 2 of the groups have warm sea surface temperature conditions. That is very similar to what we saw in the suppressed simulation. But 1 group have very cool sea surface temperature conditions, and this group has the most tropical cyclones. It has 9 tropical cyclones compared to 3 and 4 for the other groups. All right. This slide basically tells us that when African easterly waves are absent, regardless of what condition is forming the tropical cyclone, the ocean surface will always be warm. All right. But that is not the case when African easterly waves are present. Now, the next thing that we are trying to do that I'm not going to talk about in this presentation is trying to find out how the tropical cyclones in these groups were formed, whether they were formed from African easterly waves or they were formed from other mechanisms. But that is our hypothesis. We believe that the tropical cyclones in this group were actually formed by African easterly waves, and then the tropical cyclones in the other groups were formed by other mechanisms, right? But then the conclusion on this, the conclusion from this slide is very simple. The conclusion is that when African easterly waves are absent, the sea surface temperature plays a very important role in the formation of tropical cyclones. Right now, I'll just give a brief summary of what I've talked about, and then I'll try to talk about some impact or some implications on the climate of West Africa. So we have seen in this presentation that tropical cyclones in the Atlantic region will develop even in the absence of African easterly waves. And so because of that, African easterly waves do not limit the seasonal frequency of these tropical cyclones, right? And if this is the case, African easterly waves may not be reliable predictors for future changes in tropical cyclone frequency, right? And then we have also seen that there are, although African easterly waves do not limit the number of tropical cyclones, they may have an influence on the timing and then the location, the when and the where of tropical cyclone genesis, right? And then we have also seen in the last slides that tropical cyclones will develop and evolve in warmer ocean surface temperatures when African easterly waves are absent or are suppressed, right? So what are the implications of these results for West Africa? Now, somebody will argue, yeah, there are no implications for West Africa because tropical cyclones do not affect West Africa. I totally agree. The tropical cyclones do not affect West Africa. But then there could be some influence of these results that we had on the climate of West Africa. So let's try to look at that. Now, I believe most of the meteorologists and then the atmospheric scientists in this group know about the temperature of the Eastern Pacific, can know that the temperature of the Eastern Pacific can have an influence on the West African monsoon through the ENSO effects, right? Now, we can see on this control figure here that the sea surface temperature in the Eastern Pacific is cooler than the suppressed experiment. This is a classical classical representation of the ENSO effect on the West African monsoon. So during in the ENSO, sometimes the sea surface temperature of the Pacific is cooler, sometimes it is warmer, and these have influences on the West African monsoon. Now, from this study, it's going to be difficult to see what is going to happen in West Africa, but then because we did not extend our study domain to cover West Africa, so we did not investigate this. But then we know already that the temperature changes in the Eastern Pacific Ocean have an influence on the climate of West Africa. And so these result that we see, if this kind of results happen in future, it's definitely going to have an influence on the climate of West Africa. Again, this is a hypothetical statement, and it needs more investigation to be able to confirm this. Now, the second thing that I'll also say is that we also know that the sea surface temperature in the Eastern Atlantic Ocean have a very direct influence on the climate of West Africa through the monsoon flow, right? So the temperature of the ocean surface in the eastern part of the Atlantic, and then the temperature of the land creates, if there is a big difference, it creates the land sea temperature gradients, right? And what happens is that when the ocean surface is much cooler than the land, cool moist air from the ocean surface will move towards the land to cool the land. And in so doing, when the moisture gets to the land, they evaporate, form clouds, and then subsequently lead to the development of rainfall, or formation of rain that falls down, right? So we can see something similar in the control simulation, although we don't see what is happening in the West African region, again, because I don't have the West African part as part of my domain. But then when you look at the suppressed simulation, we see that the ocean surface around the Eastern Atlantic becomes very warm, right? And these warm ocean surface conditions means that when the land surface is also warm like this place, it means the land sea temperature gradient will no longer exist. And so there will not be cool moisture moving from the ocean surface towards the land. Now, if that happens, it means the rainfall that we get from this monsoon flow will no longer be possible. And so this is something that could lead to droughts. Now, again, this is a hypothetical statement based on my study. I did not extend my study domain to cover West Africa, so we might not know whether this is true or not, but this is based on the physics, just what the physics tells us, that when the ocean surface is much warmer than the land surface, then there will not be transport of cool moisture towards the land. So this is something that we can investigate in the near future. Right now, the other thing I would like to talk about, which is, I believe is very important, is how we can apply the method that I used to study the climate of West Africa. Now, I told you in the beginning that we placed a filter right off the western coast of northern part of Africa. So what if we move the filter to the eastern part of West Africa, right? So we put the filter somewhere here. If we put the filter somewhere here, we can be able to control the African easterly waves that form on the eastern side of the filter. And we can find out, we can make simulations to find out their effects on the climate of West Africa. This is something that can be done to study the impact of African easterly waves coming from Central Africa, or coming from the Central African region towards West Africa. We can try to use this kind of method to find their impact on the climate of West Africa. So for people who are interested to pursue this kind of investigations, I'll be happy to collaborate. I'll be happy to help in the research to find out how we can use this kind of method to improve, to understand the climate of West Africa. And it's not only rainfall that we can use this to study. We can use this to study other variables like clouds, temperature, humidity, and other things. So, like I said, people who are interested in this, I'll be very happy to take part in any collaborations that will happen from this kind of experiment. So at this point, I would like to thank you for your attention, and thank you again for listening to me.
Thank you very much, Doc, for the presentation. And I believe our participants will definitely have a number of questions which they would want to ask I believe those who would want to write or type in the text section, you could type a question, we can read it loudly for you. And if you have a question too, you can also raise up your hand, that we will also allow you to ask a question. So let's go straight to those who have raised up their hand. I think we have Professor Amakuchi raising his hand up. I think when he finishes his question, then Kwesi will also ask his question. So let's go to Prof. Amakuchi. Prof, kindly unmute yourself.
Thank you very much, Derek, for this presentation. In fact, you've given us an insight on the African easterly, on how it really affects the West Coast. Now, however, I saw that you did not look at the what the collaboration you are requesting, and I think that we'll be happy to have that collaboration. But coming to my question, did you look at the relationship also between the African easterly wave and then African easterly jets, and how that really affects the cyclone development? Did you look at that?
All right. So thank you very much, Prof, for this nice question. So yes, sorry, can I go on?
Yes, go on, please.
Okay. So yeah, so to increase, to decrease the African easterly waves, basically what we did was to decrease the magnitude of the African easterly jets, because this is actually what triggers the African easterly wave. So there are some slides that I did not show here that I can show you later on. We actually saw that by reducing the African easterly jets, we actually decrease the magnitude of the African easterly waves. Now, currently, what I'm trying to do is to, again, look at the relationship between the African easterly jets and then the African easterly waves. But in this case, I'm trying to enhance the African easterly jets, trying to intensify the magnitude of the African easterly jets to see how it's going to affect the African easterly waves. So we have found out by decreasing the magnitude of the African easterly jets, we decrease the African easterly wave magnitude. But we are now trying to look at the reverse to see if by intensifying the African easterly jets, we can intensify the African easterly waves too. So yeah, I have half of the answer to your question. That is the decreasing effect. But the other half, it's now that I'm doing so. Yeah, I can talk about that later with you.
All right, Prof, please, are you okay with it? Okay.
It seems
I want to make a contribution.
Okay.
Thank you. I think, yes, Derek, thank you for the answer. But I think the reverse, what you were saying, actually, African easterly jet tend to also intensify the African easterly wave. In particular, there's a publication that indicate, like, after from Africa, after moving away from Africa, getting to the eastern, going to US, it tends to rather intensify it, and that somehow intensify the cyclone development along the coast. So maybe you can also look at that, and then we'll see that. And then I was happy about the land sea breeze effect. Do you think that the land sea breeze effect, this might be contributing factor for the rainfalls that the first onset that happens most these days? Sometimes February already we are having some rains and etc. What you are explaining, I think that possibly. Do you think that possibly might be a strong contributing factor?
Exactly. That is one thing I had in mind, because recently what we are seeing is that the tropical cyclones are beginning much earlier than they are supposed to happen, because usually they start from July to the end of October. But recently we are seeing tropical cyclones forming in May. So, and some of them are even forming in some very weak African tropical cyclones are forming in before May, in April. So this could actually have an influence. But again, like I said, these are all hypothetical statements. We really need to investigate to see if they are indeed what is the causing factors involved in this kind of early rainfall that is seen in West Africa. But it really could be an effect. Yeah.
All right, Prof. I think there's another hand raised. Kwesi Green, can you ask a question?
Please, can you hear me?
Yeah, we can hear you.
Okay, great. Dr. Derek, so thanks for this very insightful presentation. I really appreciate the work that has been done here. On, I think, slide 8, you showed a plot of, I think, the relation between the African easterly waves and I think TCs, the tropical cyclones, slide 8. Yeah. I wanted to know if what we experience, like what we are seeing here, is from model runs, because I can see like the year, or it's coming from observation.
Yeah, so this study is actually an observation-based data set. Yeah, but the African easterly waves that we see here are not really from observations; they are from reanalysis products.
Oh, okay.
But the tropical cyclones that you see are actually from observations, because it's very easy to get data on tropical cyclones. Yeah.
Yeah, the reason I was actually asking that question is because of like representation. For instance, if you are using reanalysis, like how well does the reanalysis represent the region? Because I mean, people develop reanalysis data for specific reasons. That's what I was asking.
Yeah, that's a very good question. So another reason why there is this confusion whether African easterly waves really impact the tropical cyclones is that the reanalysis have different views. So when you look at the NCEP reanalysis from the United States, they have a different view of the interannual variability of these African easterly waves compared to the ECMWF reanalysis. They have totally different views. But one thing is clear, in both of these reanalyses, which are like the top reanalysis that we use for these kind of studies, one thing is clear, in both of them, they have sometimes positive correlations and sometimes negative correlations. And so that is something that we know, even if you look at individual reanalysis products. And so we know that there is this kind of discrepancy between the reanalysis products, but then the variability of the reanalysis with the tropical cyclones also have discrepancies. We don't know if it's always positive correlations or sometimes negative correlations.
Okay, great. So a follow-up question, I think there's a different question that I wanted to ask with regards to the African easterly waves, is that we are looking at waves. We know that there are portions of the wave that could contribute to cyclonic vorticity advection and anticyclonic vorticity advection. So do we think that that kind of phenomena from the AEWs can affect the intensity of tropical cyclones?
Okay, yeah, so thank you for asking this question again. So yeah, it's actually something that I did in my work, but I did not show that because, I only ran one ensemble member because it's at 3.5 kilometers resolution, so it's very expensive. But what you realize is that there was a mixed impact on the intensity of the tropical cyclone. Right, so we could see that sometimes when you look at the category 1 hurricanes, we could see there were a very high number of tropical cyclones for the control simulation, but then there were few numbers of tropical cyclones for the suppressed simulation, right? But when you look at something like category 4 hurricanes, there was a very high number of tropical cyclones for the suppressed simulation, but a low number of tropical cyclones for the control simulation. So if you just look at that, you will say that, okay, then if we take the African easterly waves out, the tropical cyclones are more intense. But we also saw that there were category 5 hurricanes for the control simulation, but not the suppressed simulation. Totally zero. So this is like a mixed feedback. Okay, so the solution to this is to make other ensemble members, which I'm currently running. So I believe you are on our group, so you can see that I'm running a lot of simulations currently. So I'm running, I think, 4 different ensemble members to see if we will be able to have a more robust interpretation for the impact on the intensity. But based on this one simulation, it is very difficult to say if African easterly waves will really have an impact on the intensity of tropical cyclones.
Yeah, awesome. That's an awesome work. I'm actually very happy about it. Please, my last question before I leave you to go.
Okay.
On slide 24. I think you are talking about the African easterly, yes, the control run and then the suppressed AEWs. I think one thing I realized is that with regards to the TC genesis, it's mainly about tracking the point where we have lower sea surface pressure, and all the other factors involved are also there. But so what actually stood out to me was that in the suppressed runs, the variability is mostly located in the northeastern part. And from your results, you could see that on the PDF plots, you could see that the shift of the TC genesis had moved northward.
Okay.
So probably that could be, it's just an idea that came to mind that probably the AEW's absence could cause the TCs to be shifted up because there's variability more in the northeastern part of the SST as compared to the southern part of it. Because I mean, if all the temperature is the same, we know temperature has a relation with pressure, so probably the pressure would not be varying as much and TC genesis would be difficult. It's just an idea that came to mind.
Yeah. Okay. So thank you for that idea. So there is also another view for this. So we have the 2 tracks of the African easterly waves. What we know from studies in the past is that the southern track of the African easterly waves is most effective in developing into tropical cyclones. But if you look at what I have on this slide, we can see there is more tropical cyclones being formed in the northern part of the region. Now, that does not mean the northern track tropical cyclones are more effective. What really happens here is that there are fewer southern track African easterly waves, and there are more northern track African easterly waves. So the ratio is like 1 to 10. So if we have 1 easterly wave here, it's going to develop into tropical cyclone in the south. If we have 10 tropical cyclones here, only 1 is going to develop into a tropical cyclone. All right. And so the shift to the north really does not really concern the African, I don't think it really concerns the African easterly wave strength over here. But it's just what this basically tells us that the southern African easterly wave track is the most effective in developing into tropical cyclones. That is why there is this shift from them. Okay, so those African easterly waves no longer develop into tropical cyclones, but the northern tracks have some African easterly waves that still develop into tropical cyclones. Yeah.
Okay.
Yeah.
That answers a lot of things. Thanks a lot.
Yeah.
And
Thank you.
very nice work. Thanks.
All right, thanks. We see we now will wait for Dr. Ayi. I think he rose up his hand. If he's not ready, let me go straight to the
hello
question. Okay, you're ready.
Yeah.
Okay.
So that was a great work. I mean, that's a great work, Derek. Just a quick one. I mean, so you're talking about the AEWs and then their magnitudes and how they impact on the TC, genesis, and then, its movement. There were instances where I was out and then I had to join in. So I wanted to know if, definitely waves have some other properties. Okay, so for instance, you're looking at the period of the wave. I mean, how the wave itself is tracking, how it also would impact on the TC. I don't know if you something on that, and also if maybe the amplitude of the waves, particularly when they are leaving the shores of the West African coast, okay, whether that also impacts on the, the track of the TCs, and then also even the size of the TCs and other dynamical properties of the TCs. Yeah, and maybe let me just lump everything together. I think the first part is also based on partly what Professor Mekuji also asked. Yes, and then the second part, and I think I heard you give a hint of some possibility of futuristic drought if let's say AEWs are still like if they are able to influence TCs. Am I right?
Yeah, of course, you are right.
Oh,
But
okay. Sure.
so can I go on, or you have other things to say?
Yeah. Okay. So the reason why I was asking, I mean, so I think in the current study we are doing, and we had to review a couple of literature, and one of them was based on the Sahelian droughts in the 70s and the 80s, and one of the studies was talking about possibility of a reversal in the oceanic phases. Mostly we would expect that. With warmer surface waters, definitely we should have some lots of precipitation activities moving inland and all that. But mostly if that is reversed, then it means that also reverses the Hadley circulation.
Yeah.
So on the aspect of possible impact of the outflows of the AEWs influencing the TCs and how it impacts, let's say, weather features over West Africa, I believe maybe that's one aspect to also look at. Be focusing on the circulation dynamics, and then maybe that could give some more detail on how realistic those maybe findings of potential droughts and the rest could be.
Yeah.
Thank you.
I totally agree with you with that. So yeah, it's not something that I have done, but then when I was invited for this presentation, I started thinking of how these results could impact the climate of West Africa. And when I looked at the plot, I realized, it's very clear to me that when you just think of the physics, circulation patterns and everything, there's probably going to be some kind of differences in the region. And so that's why I mentioned in the final slide that people who are interested to study this, I'll be happy to assist, and I'll be happy to collaborate with people on this. So yeah, I believe there is some kind of influence on the West African climate that you mentioned through the circulation. So yeah, it's something that hopefully we can look at in the near future.
All right. Okay. And then the first question on the of the amplitudes and then the other parameters. Yeah.
So when you look at the period and then the amplitude, I believe that we took care of it. So when you look at this slide, so I did not really talk about a lot that went into the filtering. So the filter that we use, which is called the Lanzos filter, was used to remove the 2 to 10 day time scale from all of the variables in the boundary conditions. Okay, so some of the African Easterly waves have a period of 3 to 5 days, and then some other studies have shown there is a second group of African Easterly waves that have a period of, I think, 6 to 9 days. All right, so to be able to get all of these African Easterly waves taken care of, we took the 2 to 10 day time scale. We removed the 2 to 10 day time scale, which effectively removes all of the African Easterly waves from the information that we have, the forcing information that we have. And then the amplitude issue is what really impacts the strength of the wave. So like I mentioned to Professor Mekuji, we reduce the African Easterly wave amplitude. That is by suppressing it. That's what we did. But the other thing that we did not do, that I'm trying to currently look at, I'm actually thinking of how to do it, is how we can increase the amplitude. And by increasing the amplitude, we are basically increasing the intensity of the wave, or the intensity of the jets, which also will increase the intensity of the wave. So it's something I'm currently thinking of how to do that. It's not straightforward as suppressing the African Easterly waves totally. But the suppression is quite simple. We just put a filter to remove the variability. But then intensifying the amplitude is a bit tricky for now. So it's something I'm thinking of. And if you have any idea to share with me, I'll be very happy to work with you on this. So
Yeah, so I mean, the reason why I was a bit concerned it was in increasing the jet speed. I mean, let's think of it as, say, we have a feature and that we are pushing against it, all right? By that, we may or may not increase the amplitude. Okay, so that's the aspect of maybe concern for post-study beyond this one. So I don't know if it's best to first and foremost do an observational analysis of that based on some records of AEWs and then some of these TC occurrences. So at least we do that by, I mean, particularly looking at, I mean, the exit point of the AEW from Africa, because we know that at that transect, they are moving from the land onto the ocean. So definitely once they move onto the ocean with the increase in SSTs, which is likely to intensify more in the mid part of the Atlantic, then they would spread out. So if they're already bigger and the SSTs are more intense, then they might make them more intensive, right? They become more intense. So maybe I think it will be more an observational component of a study first, then based on the findings, then the model can support that.
To support, exactly. That's really great. That's a good idea.
Sure. But then thanks for the presentation, and it was a very insightful one.
All right, thank you very much.
All right, thank you, Dr. Aye, for the question. I think I'm going to the messages. There are a few questions, hands raised, but I just want to look at the questions, the message, so that we can really answer that one too. The question was, what is the filter made of? How effective is the filter in suppressing the AEW? I think this is coming from Engineer James. So could you answer?
Okay, thank you. Yes, I mean, if you remember, I changed my computer right before the presentation. So I will not be able to show the full picture of how effective the filter is. But basically, a proxy for the African easterly waves is the meridional wind, usually at 850 hectopascal level or at 700 hectopascal level. So what we did was actually to compare the meridional winds in the control simulation and then the meridional winds in the suppressed simulation. And you could clearly see that there is a reduction in the magnitude of this meridional wind. And that's what shows the African easterly wave suppression actually worked. Now, when it comes to what the African easterly wave, the filter is made of, it's, I mean, it's just, it just looks at the information that we have for the winds and for the other variables, and then just take away, it's like smoothing the 2 to 10 day time scale. This is something very simple that we do in mathematics, like something like moving averages. But it's not really moving averages, but it's just, that's the idea. You are smoothing the 2 to 10 day time scale in the information that you have, because this 2 to 10 day time scale is what contains the African easterly wave information. So when we remove this 2 to 10 day time scale from the information that we have, we effectively get rid of the information on the African easterly. So that's basically how this filter works.
All right, thank you. We also have Maureen. Prof, we'll come to you later, but we want to allow the ladies to also come in. So Maureen, can you come in?
Hello, Dr. Derek. Thank you very much for your presentation. I think during your presentation, you mentioned that, I don't know whether I got that clearly. You can re-emphasize that for me. That's in terms to say you've noticed your thesis are, in recent days, are becoming more like they generate early. Is that right? Or I didn't get it?
Yeah.
Okay. So if that have been identified, during the control or the experiment that have been done, were you able to establish the months? I think you did your simulation between August to October, right? If I did. Yes. So were you able to establish, let's say, looking at climatologically, what is the month period in which these waves are more intensified to produce these theses?
Okay, that's a nice question. So we have, when you look at the variability of the waves, so like I mentioned, you have two tracks of the waves, and these two tracks are not on the same vertical level if you look in the atmosphere. So one of the tracks is most intense around 700 hectopascals, and the other track is, I think, most intense around 850 hectopascals. Now, there is a study that I referenced here. This particular study, he tried to look at when the African easterly wave is most intense, and he found that for one of the tracks, it peaks, the peak of the African easterly waves is in September, and then in the other track, the peak is, I think, in August, right? And if you look at this period, this is when in September is when we have the maximum number of tropical cyclones occurring, or sometimes the most intense tropical cyclones occurring, and they correspond to this African easterly wave seasonal variability as well. And so we can tell that from the African easterly waves, we can also see the pattern of the tropical cyclones. The only issue is that sometimes the African easterly waves do not occur when we expect them to occur. Okay, sometimes they occur way before the tropical cyclones form. And other times too, we can have tropical cyclones occurring before the peak of the African easterly waves. And that is why we have this confusion whether they really control the seasonal and the seasonal variability of these African easterly waves. But for the 2020 season that I looked at, when we looked at the observations, the informations that are available, you could see there was a link between the tropical cyclone number and then the African easterly wave number as well.
Okay, so I think I really wanted to get, like, were you able to establish like yeah, I know you talk about the variability, which is real, which does happen, but like, were you able to kind of identify like this period are really mainly the like period which within this from, let's say, May to October are to be looked at specifically, let's say, to maybe forecasters or researchers who are studying this to be able to advise on impact or something like that? Be able to kind of identify a month's period that around this period, this.
No. Okay. Okay, so yeah, we did not really look at certain group of months. What we looked at is the August to October period, and this is what we know already. This is the most intense period for the tropical cyclones from August to October, and this is consistent every year. That is when we have the most intense tropical cyclone. So if that is what you are asking, we selected this period based on what you know from before, but we did not we did not identify a time period that we should probably have a look at. But if we want to study African easterly waves and then tropical cyclones and probably their effect on the climate of West Africa, then I will suggest that we look at all of the rainy season. I mean, starting from May to perhaps November, because all of this period can have African easterly waves, and there could also be tropical cyclones. And I believe we should look at all of this period together. We should not really isolate a certain month and try to look at that month alone, because something could be happening in other months that we don't look at. So if that's what you're asking, I don't know if I answered your question.
Yeah, I think you've answered it for me now. Yeah.
Okay.
Yeah.
Okay,
So
thank you.
You're welcome. I think the only thing I also want to add to it in terms of like the collaboration you're calling for, maybe further studies for West Africa, I also recommend that we also look at the tropical easterly jets as well as the subtropical easterly jet.
Exactly.
Not
They
many
are all important.
researchers really look also into the tropical easterly or the subtropical easterly jets. So because they in a way also really influence this easterly wave formation, how it will be strengthened, and also are being affected by the upper level at dynamics. So I will also recommend that is also being studied as well. Also, what as the depression, the mid-latitude depression from the dry air or cold air that move across the continent, especially for West Africa. Yeah, thank you.
Yeah, that's a very good recommendation, and I will add something to that. Yes, of course, we have to look at this tropical easterly jet, because if we increase only the African easterly jets, we also kind of increase the wind shear. And one thing that is not very good for the formation of these tropical cyclones is high wind shear. And so if we are trying to intensify the African easterly jet, we should also think about how we can balance it by intensifying the tropical easterly jets and the other jets that are available. So that's a very good recommendation, and I believe something that we take on board.
Yeah, thank you so much. Prof. Makuji, please, can you come in? I think you had a question.
Okay, thank you very much. Mine is not a question by just a question. I think that so your talk, the talk has really generated a lot of a lot of unknowns, a lot of things that we really have to investigate. And I will task the team to kind of put these things down so that we can have these as we moved on. Definitely we'll have students so that we can pick on some of these topics and work together. That's the first thing. Then the other thing is about the amplitude. You realize that it exits from Africa. When if it intensifies, definitely that results into a cyclone. Most of them. How have we studied? So I think that there might be some case studies that we have to look at. We have looked at situations where we see it and see its effect even within West Africa, and then after, and the post effect, how it into the ocean. Definitely, warmer oceans, we expect it to intensify. If the ocean is warm, we expect intensification, and that can definitely move on into the ocean. So these are some of the things that I think are very interesting. As we also know, you showed also that the sea surface temperature play a very significant role, which is excellent, so in general, this is what I want to say. So it's more of a contribution I want to add, that your excellent thing. Let's put things down so that we can get started. Thank you.
Okay, thank you, Prof.
Thank you, Prof. Too. There's a question in a text message, and it's from Christian I. He says that in the absence of AEW and SST, so he said in the absence of the AEW, SST plays an important role to TC. So what is the threshold of the SST?
Okay, and that's a very good question. So we already know. I mean, there have been studies in the past, decades ago, that have shown that the threshold sea surface temperature that leads to the development of tropical cyclone is 26.5 degrees Celsius. Recently, there have been other studies that have debunked this threshold. Some other studies have shown, and even from this particular study, some other studies have shown that when there are other favorable conditions, this SST threshold is not so important, and we can have tropical cyclones that are forming even at 24 degrees Celsius. Now, if you look at some of the results that I showed, for instance, the last slide, I believe, if you look at this result, this first control figure, this is, we have 9 tropical cyclones forming in this case. If you look at the sea surface temperature values in most of the region, except around the eastern part of the United States, we have the sea surface temperature less than 26 degrees. Okay, so studies have shown again that these sea surface, these tropical cyclones can form in temperatures much lower than what is known to be the threshold sea surface temperature value. So the threshold is like I mentioned, it's what is known, but recent studies are showing that we might have to revisit this sea surface temperature threshold value that has already been found in the past. So currently, I will not really say that is the threshold, but I mean, if you look at the books and the articles, that is what is written inside. Right?
All right, thank you so much. Prof, sorry, okay, I think Prof was ready. Dr. Derek Danso, please, can I say a take-home message from your presentation today is AEWs may thus not be reliable predictors for future changes in the tropical cyclones?
Exactly.
Okay, all right. So I don't know whether there are any other further questions that have been posted, and then I've not seen any hands also raised yet. Yeah, however, we are so pleased with your presentation and everything. So I think for now we need to take a picture to be able to keep records of those who have. Oh, I think there is a hand up. So I'll allow him for just a few minutes then. Ibrahim.
Yes, good afternoon, everyone.
Yeah.
Just want to say some words about my colleagues, just to tell him that I'm really happy for seeing him presenting such great work. So congratulations, Danso. Yeah.
Yeah, thank you, Lali.
Thank you very much. We are proud of you. All right.
Thank you.
Okay.
All right, thank you so much. I want us to turn on our camera so that we can take a few pictures. Thank you so much for participating in this session of our 9th meteorological webinar series. And we are going to have another one hopefully next month. And I believe you also join. This is just the beginning. We will have a lot of presentations this year. So I'm just trying to whet your appetite because there are more interesting topics also coming on board. And then if you have any questions, you can also direct it to the emails that sent you the invitations, and also you can also contact our presenters because they are always available. We are going to make available the video recordings of this particular session to you as usual. And then you can follow up afterwards if you have any other further questions. Thank you so much.
Sami, can I say something before we go?
Okay.
It seems some people are trying to get in contact. So probably you should, if you can share the email for them to contact it, I think that would be great.
Sure, we are going to do that. Yeah.
Okay. Thank you very much.
Okay. All right. So I think there is no further question. So we again thank you so much for participating. We believe the next time we call upon you, you are not going to hesitate. You will come on board and then everything becomes so smooth. Thank you so much.
Thank you.
Bye-bye.